want to talk about putting fuses into parallel circuits and how we actually select a fuse for a parallel circuit. I've got a really cool example here. I've got a lighting system for a vehicle. So whatever kind of vehicle it is, could be a tractor, could be a car, could be a truck, whatever it is, doesn't really matter. But the thing is, it does actually have brake lights, and it's got like some running lights or some tail lights, and it's got some headlamps. What I'm going to do is check out how to actually put fuses in here. Plus, then I'm going to want to add some things in, and we'll talk about the logic of how we would add things in. More specifically, like where would we put a switch, and how would we wire things in if we wanted one switch to control two things and another switch to be independent and maybe two other switches kind of doing something else. So let's just jump into this and take a look at this example. So what we've got here is it's a parallel circuit. Actually, all of these loads, yeah, that's a word I use for resistance. I mean, this is a lamp. It does work. It's a load. All of these loads have resistance, and actually they're all in parallel. So they're all pulling battery. They're pulling current right out of this battery, and the potential voltage across each one of those is 12 volts all the way along. So actually, all loads, except for maybe a radio circuit in your computer and some other things, like fancy things in your car, are all 12 volts. The fan, all the motors, the power seat, whatever, everything in your car is working on 12 volts. Let's say like an old car that runs on 6, or maybe an older diesel that runs on 24. But there are different voltages that for different specialized vehicles. You know, forklifts, they're all power and they run on like high voltage, like 48 or even higher voltages than that. But let's just talk like a normal vehicle that you get in and drive and it's got brake lights. Okay, good. So let's continue here. What we've established is we know all of these have 12 volts drop across them, or you know, the potential that's pushing those electrons into these is actually 12 volts. So I'm just going to label that. This could be 12.7 volts. And the reason I'm putting 12.7 is actually if you fully charge a lead acid battery and just kind of let it sit there like it's like fully charged, it's actually around 12.7. You can push them a little bit more, and depending on how tired they are, they may be a little bit less. But if it's still a pretty good battery, it'll be somewhere around 12 or more volts. When the charging system is happening and there's an alternator in the car, when that alternator comes on, it goes up to like 14 volts, maybe a little bit more. You may have some regulators in your system that if there are some things that are sensitive to high voltage like that, maybe there's a regulator say, no, this thing gets 12 volts only. We're not talking about regulators right now. I just want to say that as the alternator charges, it kicks the voltage up. Sometimes the voltage goes up to 14 volts. Depending on the type of control system and the age of your car, that fluctuates a little bit more or less. So we're going to calculate all of our fuses on actually the rated voltage for the battery. So 12 volts, we're going to roll with that. Anyway, so what's going on here is that I've got this circuit here where I've got my brake lights with no control. It's interesting. And I've got my tail lamps and then my headlamps, and I can see that the control system is like this. If I close this switch, that's just for the lamps. That's for all the lights. Now, it doesn't mean that if I close this, all of those lights come on. You can see that. There's a switch here. This switch only controls the headlamps. And you guys know that when you get into a car, you can do like kind of one turn or whatever thing you use on the little dial on the turn signal thing, or there's something on the dashboard or wherever it is. It's kind of one turn just for the taillights. And there's another turn where you can turn the headlights on. So what we're going to take a look at is these two options here. So this turns the taillights on, but it doesn't turn the headlights on. So actually what I'd probably want to do here is I'd want to put maybe a selector switch in here, and there are different options for that. But let's just kind of look at this logic here. So I can say that if this is called switch 1, and this is switch 2, the logic here is if switch 1, then taillights, for sure, period, hands down. The other logic here is if switch 1 and switch 2, then headlamps. Actually, more like if switch 1, taillights. So in association with, hey, how do you turn the taillights on? Oh, just switch 1. If switch 1, then taillights. And then here, headlamps. Well, if switch 2, headlamps, you can't say that. You've got to add more logic in. So for the logic for turning the headlamps on is it's if switch 1 and switch 2, then this. I mean, I could put an OR in there, but it would just kind of be silly. So I'd have to rewire it for an OR, but that's not what's going on. I don't want to just have my high beams on, or my taillights, or I don't want to just have my running lamps on. I mean my headlamps. I can't get my word around the headlamps. Okay, so I don't want to have just my high beams on or my headlamps on. Now that'd just be weird. I want to have my taillights on kind of first, and then have my headlamps on. So that was actually part of the design. The designers of the cars wanted to do this. They didn't want to give you the ability to just turn your headlights on. They want to make sure that if you actually go to turn your headlights on, you're forced to turn your taillights on as well. So that's part of design. When we design a circuit, we have to think about the logic of how we want to apply the logic in here. But where do we get the logic from? Well, we get the logic from the functional requirements of the circuit. And the functional requirements are often kind of, how it works in the environment. So whoever's designing this circuit originally, kind of the first guy who actually started putting taillights and headlights on a car, probably the first was just one switch for each. That would have been an OR. But then someone got smart and said, hey, I've noticed that some people are just turning their high beams on without their taillights, and if it's dark out, you want your taillights on. So someone designed a switch that click, 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 or maybe two switches or whatever it is. So they put some logic into it, and that's how it came in. So you have to think about that when you're designing any kind of circuit. You have to put the switches and the control in a certain way where you can put in, okay, this condition can only happen if these things are happening as well. So real simple kind of logic here. Let's go on to selecting the fuses. Okay, so now what I've got here is that I don't have anything here. There's a break here, and I'll tell you about that in a second. But I've got like an independent fuse here. Now, this fuse is for all of these lights. It's for the tail lights and the headlights. So I'm going to put a fuse in here, and that's my symbol for a fuse. I don't know what size of fuse to put in there, but I'm going to do some calculations. Okay, good. So I don't know what size of fuse to put in there, but I'm going to do some calculations. Okay, good. So I'm going to put a ground here, and then ask you, is that good? Are we good? Good to move forward with that? No, the problem is, in this case, the ground is going to be a problem because as soon as I even just wire the headlights up, the tail lights, the brake lights, they're going to come on all the time. So what I'm going to do here is, I'm going to put some control in here. And the way we control brake lights is like this. You put a normally open push button. So this is brake lights. This is the brake and tail lights and headlamps. Okay, good. So these are brake lamps. Now, what you want to do is, this is kind of a little bit weird, but you want to put a normally open push button on the brake lights. But the switch to power these is before. The switch to power these is before. Why am I putting the brake light here? Well, the reason I put the brake light there is because, you may not know this, but the brake light switch is actually on the brake pedal itself. So when you press the brake pedal down, what it does is it actually it activates a switch. And what's going on there is that actually it's switched right to the ground because the switch itself is actually connected right to the body, right to the actual metal of the ground itself. So the great thing about automobiles is that the physical ground, or the physical body itself, the frame and the body and the chassis and everything is made of metal. So that's actually hooked directly to the battery. It's pretty cool. So actually I just thought about something. Hold on, bear with me here. I'm going to go for 12.0 now, just for our calculations. Because I actually did the pre-calculations here with these values, so I want to use 12. But I will digress. So we've got a control for the brake lights, and what we want to do is we want to have the normal condition for that switch to be open. Absolutely, it's very important. Okay, there we go. So in this way, I can leave my tail lights on. I can leave my headlights on. It's my problem, it's my fault for draining my batteries, but I shouldn't be able to leave the brake light on because if I'm driving down the road, I don't want to leave the brake light on. Now, let's talk about control here. Now, wait a second. There's no switch before this, but there's a switch here. This means actually is that there's a switch here, and these brake lights are not dependent on this switch at all. So this says these brake lights work no matter what. Actually, if I was going to put an ignition switch in here, I'd put it here. And the reason I put it there is because my brake lights have to work no matter what. I remember, I don't know if you've ever been to a drive-in theater, but I remember going to drive-in theaters when they existed. They're still around. And every once in a while, somebody would hit their foot on the brake, even though the cars weren't even running. The brakes would still come on. And I thought that was cool. Actually, I remember asking my dad about that when I was a kid. So what's going on is that brake lights are independent. The safety system, like it's complete, the brake lights are directly connected to this. I mean, there's a fuse here too, but there's no other control before the brake lights. So I'm gonna put an ignition switch in there. I kind of just snuck it in there. Now wait a second, I've got this fuse. This fuse is just for the taillights and the headlamps. This fuse is just for the brake lights. Okay, good. So how do I calculate the size of these fuses? Well, what I do is, I do the math, use Ohm's law, and maybe some resistance calculation formulations for parallel circuits, and I find out how much these are drawing. So how much are these loads drawing from that battery? And then I say, okay, well, I want to make sure that I put a fuse in there that's more than what they're drawing. If they were drawing exactly 10 amps and I put a 10 amp fuse in, boom, it would blow right away. I want to put a fuse that's in between 15% over and 35% over. So kind of aim for the middle there, but you're not always going to get exactly in the middle. So it's okay, we'll go through that process. So let's do the math to figure this out. Let's do the brake lights first. Okay, how do I figure out how much these are drawing? There are two ways to do it. I can calculate this using Ohm's law. I have the voltage and I've got the resistance. I can calculate this using Ohm's law. Using Kirchhoff's law for a parallel circuit, I can just add those two together and then I'll have the total. What I'm going to do is I'm going to do it kind of still in two steps, but I think it'll be a little simpler here. So I'm going to do this. RT of the brake lights equals I'm just going to call this R1, R2, I'm going to go here R3, R4, R5, and R6. Okay, good. So that's R1 to the negative 1 plus R2 to the negative 1, all to the negative 1. Okay, so I'm going to put my values in here. That's 5.8 plus 5.8 to the negative 1. I'm going to write ohms. Because I'm showing you guys how to do your documentation. Just do it like this. Put units in. Okay, so what's this answer here? Well, it's 5.8 divided by 2, but I'm just going to go do this. I'm going to go bracket 5.8 inverse plus 5.8 inverse bracket inverse equals. Nice, easy, simple number 2.9. Okay, I can work with that. 2.9 ohms. Okay, good. So now I'm going to calculate the current that's being drawn here. So I'm going to say I brake lights. I'm just going to use Ohm's law. I is V over R. I mean, it's just Ohm's law. It's that simple. So the current that's going through here is being drawn by both of these. So the total resistance here is the thing doing the drawing. So in this case, I'm going to go Vs divided by this value here, RTB, and that's going to be 12 divided by 2.9. Now, I think I showed you this before. I got 2.9. It's already in my calculator. I'm actually going to just divide it by 12, hit enter, and then hit the inverse key. It actually saves me pressing a button. I don't know. It saves me retyping in 12.9, and you know, if you could get an error there. So anyway, that's what I do. And that, whoa, that's, hold on. This is like 4.3 something. So it's 4.1379, blah, 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 whatever amps. Now, I'm going to round this off, the number after the 3. You know what? This 9 has no bearing on the rounding off. It doesn't even need to be there. I'm going to get rid of it. This 7 means that's going to be a 4, period, hands down. That's it. So, 4 amps. Okay, good. So, now, with that said and done, I'm going to keep this number in my calculator. So, what I want to do is, can I put a 4.14 amp fuse in here? Well, the answer is no for 2 reasons. One is you're not going to go and find a 4.14 amp fuse. They don't exist. I mean, you probably go to the manufacturer and have it made. It cost you a lot of money. It would be a little bit ridiculous because it's not that, you know. Fuses, we just got to go over a little bit. So we go 15% over to 35% over. So you know what? I'm going to multiply times 1.15, 15% over, and that's 4.75. Okay, you know what? I'm gonna go back to that. I'm gonna divide that by 1.15. So I get my original current, right? Then I'm gonna multiply times 1.35, and that's 5.5. So do you know what? If I get a 5 amp fuse, that's somewhere in between 15% over as far as the current goes, and 35% over. So that's perfect. So what I'm gonna do is I'm gonna label this guy. I'm gonna say I'm going to put a 5 amp fuse in there. It's very important that I label everything that I do, because someone else is going to read this. It's going to go build your thing, right? So whatever you design, you have to be accurate in what you're writing. So especially in like a report documentation, you got to label everything. So I want you guys to make sure you label everything. And you know what? I labeled this brake. I forgot to label that brake, and it was kind of a last minute thing. Actually, I had erased that before. I had erased that whole thing and redrew it, and I had a nice brake here in red, which was cool. So let's do the tail lamps. We're going to do the same method for the tail lamps. But wait a second. This fuse is not there. Oh, really? Yeah, labeling is so important. What I need you guys to do is, after you do your work, go over it again. It's always important to go over it again. And also, you have to think about, you have to stand back from your work. Just, you know what? Also dummy proof it with somebody else. Get somebody else to take a look at your work as well. So not only am I going to make mistakes, but you're going to make them as well. So always think about, stand back from your work. This is 5 amps because this guy has nothing to do with the brakes. Good. Thought I'd just mess with you a little bit there. Okay, let's go on. Let's continue. What we're going to do is we're going to take a look at this. I want to know how much to rate this fuse. What's going on here is that all of the current going to all of these is going through this fuse. So I need to know the total resistance of everything here. I can do two things. I can calculate the total resistance of this, find out the current, the total resistance of this, find out the current, and then add them together. Or I can just find the total resistance of everything and use that. Or I could find the current here, plus the current here, plus the current here, plus the current here. Lots of different options. Again, the simplest way to go is just do what I did over here. I'm going to find the total resistance here, and then I'm going to calculate the current. 2 steps, nice and simple. Okay, good. So what's going to happen here is that I'm going to call it resistance total of all of the lights, and that's going to be R1 to the negative. You know, I'm going to sneak this over a little bit. The resistance total of all of the lights equals bracket R1 to the negative 1 plus R2 to the negative 1 plus R3 to the negative 1 plus R4 to the negative 1, all to the negative 1. Okay, good. I'm going to put my values in here. So that's 8.6 to the negative 1 plus 8.6 to the negative 1 plus 2.6 to the negative 1 plus 2.6 to the negative 1 bracket ohms. I'm going to put my unit in there. Okay, good. So that is, just going to do the math. Nice and simple and quick. Bracket 8.6 to the negative 1 plus 8.6 to the negative 1 plus. Yes, I could have typed in 4.3 because the resistance of these two is 4.3. Actually, the resistance of these two is actually 1.3 as well. So I'm just going to keep rolling with this. Okay, good. Plus 2.6 to the negative 1 plus 2.6 to the negative 1 plus, bracket, and then to the negative 1, enter, and that is, ooh, that's pretty small. It's 998 milliohms. Now I'm just going to check it again. Is that right? Well, it's okay to double check things. Okay, bracket. Wait a second. The total resistance is going to be definitely less than this. Actually, the resistance of this is 1.3. If I'm adding more resistance, it goes down. So yeah, maybe it is actually below 1 ohm. I'll do this again. So it doesn't hurt to just do this again. So in this case, 8.6 to the negative 1 plus 8.6 to the negative 1 plus 2.6 to the negative 1 plus 2.6 to the negative 1. Bracket negative 1. Bracket, ooh, yeah, bracket negative 1. Ooh, bracket negative 1. Again, I actually did that by real mistake. Step back. Okay, good. So here we go. Now, that answer is, oh, it's the same answer. Okay? So, I'm going to write this down. This is going to be 998.21 milliohms. 2.1 milliohms. So, you know, I ask all my students to give me 2 decimal places, whether you do that on your own or whatever, but that's what I want for my students. I always want that for my students. So that's what I'm writing here. Okay, we're good. So now that's my current. I mean, that's my resistance. Now I want to find my current. I'm keeping this value in my calculator because I know I'm just about to use it next, right? Here we go. So what I want to do is I'm just going to kind of split this up a little bit here, and I'm going to do this because it's getting a little messy, but I want to sneak it in here, okay? So I'm going to say my I for my lamps is going to equal to the voltage source divided by the resistance total of the lamps. And in this case, you know, I'm not even going to do the math because it's simple, but I'm going to show you this, what I'm going to do. I got 2 things. Actually, I better write this down. I'm going to go 12 volts divided by 998.21 milliohms. Sorry, I'm writing a little, it's hard to write on an angle. Here we go. So now this number's in my calculator, but I have to type 12 into my calculator first. So what do? Watch this, you'll love it. I'm going to hit divide by 12. Isn't that the inverse of what I want to do? Well, yeah, there's an inverse key. Now I'm just going to hit inverse. I do this all the time. Really saves a lot of work. Oh, 12.02. Oh, that's interesting. 12.02 amps. Now, if all of these are drawing 12.02 amps, and that fuse there, well, wait a second, I'm just going to keep that number in my calculator. I'm not going to get rid of it and type in 12. I'm going to multiply that by 1.15, and that is 13.82. Okay, you know what, I'm going to divide that by 1.15, gives me my original number, gives me that number back. Then I'm going to multiply by 1.35, and that gives me 16.2. You know what, 15 amp fuse is in between those 2 numbers. Guess what, they're readily available. Pretty common automotive fuse. So what I'm going to do here is I'm going to say, oh, okay, this is going to be 15 amps. Okay, good. So we know how to do all of that math. We know how to calculate it. We know how to choose our fuses. So I'll tell you a little bit about, as I erase this, about different availability for fuses. Now, below 1 amp, fuses come in all sorts. You can get a 100 ohm. You can get a 100 milliamp fuse. You can get a 200. You can you get a 300? I don't know. I don't have any in my kit, but you can get a 400, a 500, 600. I've never seen a 700, but they probably exist. And certainly you can get an 800 milliamp fuse, and you get a 1 amp milliamp fuse, and you could probably get a 900 milliamp fuse. I haven't seen one, but they probably exist. So fuses go like this: 1 amp, all of those things below, and then you got a 5 amp, jumps up to a 10 amp, and then a 15, then a 20, 25, 30. And then from there, it usually jumps up to, I think there are 35 amp fuses somewhere. Imagine you can get them. But in automotive, it just jumps up to 40. Okay, good. So now, what I want to do is I want to talk about control, and then I'm going to let you go. Just bear with me for a second. We talked about, you know, fuses and stuff, and we know how to calculate the right fuses. Now, we talked a little bit about logic here. I want to add some more logic. Let's say I wanted to put interior lights in here. Okay? So, the interior lights, should they be dependent on the tail lights and the headlights? Well, the answer to that is obviously no. Should they be dependent on the brake lights? No. They should actually, you know, if you open your door, you shouldn't, you know, oh wait, should they be dependent on the ignition? Well, the answer there is actually no. It shouldn't be dependent on the ignition. What I'm going to do is something a little funky. I'm going to take a line from here, and I'm going to run it down here. I'm going to go over here, and I'm going to go up here, and I'm just going to start kind of a new rail, okay? This is power here, directly from the battery. So I know that I want my interior lights to run on. The ignition shouldn't have to be on. I just want to open my door and the lights come on. Okay, so what does that look like? Well, I'm going to run it down here because I'm actually going to put something else in here. You know what? I'm going to put a fuse on them. And if you open up a fuse panel, there will be a fuse in there for like interior lights, accessory lights, or something like that. Now, what I'm going to do is I'm going to probably need to run several of these lamps. There's probably going to be a whole thing over here where there are going to be several lamps, and maybe I've got some interior lamps that open with the front door and some interior lamps that open with the rear door. Oh, I don't have any control in here. So I'm just going to do this and this, and maybe right now you're finally getting and understanding the need for these symbols. Because if I needed to run each one of these back to here, it'd be a mess. So there's that. Now these could be like the lights in the front, and then I can have another couple in the back. So I would actually have to put a door here. Now what kind of switch is this going to be? Now let's see, let's get this. If I open the door, so the event is door opens, I want the lights to come on. So I want a switch to become closed when I open the door. When I close the door, I want the switch to become open. Yeah. So I'm going to use it normally closed. Okay? So I'm going to do this, I'm going to put this here, and I'm going to do that. So I've got this is a normally closed switch. So when the door is closed, this will become open and the lights will come on. When I open the door, this will go into its natural state, which is closed, or its normal state, and turn the lights on. So that's a pretty good thing, and of course I'd have to calculate what kind of fuse I would need. I would probably want to have a couple other switches here, because there's a switch in the back, and maybe the switches lights on the door. Then, you know what, some cars have like exterior lights or something, or I've actually, in my old Lincoln, I've got these cool lights on the side of the door, so when you open the door, like that the inside has a light on it, so people can see. So that's cool. What I want to do is I want to add one more thing and I'll let you go. High beams. Now, high beam will come on most cars. If you just get in the car and you pull that handle back. By the way, in the olden days, like probably mid-80s, they disappeared. You used to have a floor switch. Remember those? Yeah, some of you do. That's really good. Yeah, I kind of remember those days. Yeah, when there was a switch on the floor, and you'd hit your foot on the floor, and it would turn on and off. It was pretty cool. But I've got, actually only one of my cars has that. So it goes back. It's a long time. So sadly, it's gone. But it's kind of cool that you pull the turn signal in. It's actually more efficient. But it's not as cool. But anyway, so what's going on is that most of the time, if you get in a car, whether the ignition's on or not, if you pull that, the high beams will flash. What does that mean? Well, it means it's not connected to this switch. It's not connected to that switch. And the only switch is that the logic is that it's its own switch. Now think about it, it's a high beam. So the high beam, when you pull it, it's going to come on. Okay, that's fine. So what's going to happen here is that actually I am going to put a normally open switch. You know what, I might just kind of run over here and I'm going to put some high beams over here. Okay, I'm getting a little bit messy here. You know what? And they can share a ground. Actually, these all could share a ground. These two could share a ground. These two are actually kind of sharing one ground anyway, but they have to go through here, so they have to share a ground. However you look at it, this is high beam. Okay, so that's a high beam. Now, I can do this and do it. But you know what? There's also a switch for the high beam. Like an actual, like, click, and they stay on. Right? Because you don't want to have to like hold that all the time your high beams are on. So how do we integrate that into here? Well, guess what? The high beam switch only comes on if the headlight switch is on. So what we need to do is this. We need to run this from here down to here, come into here, and we have to go into here. And we have to connect to there. Now we created a problem, but we also created something really cool. We've created an OR. Now, get this. The high beams can be activated or turned on from this. That's that, right? So you want to flash somebody, yeah, go ahead, you can pass me, or tell the truck, yeah, you can go ahead and come back in. Whatever you need your high beams for, just a it's good. Now, the OR is this, or you can turn them on permanently by just doing that. So that's really cool. Now, before I let you go, I'm going to ask you, what is the problem here? We just created a problem that now we have to go back to the drawing board and solve. And the secret to this, or the hint to this, is high beams are even brighter than headlamps. Watch this. 1.8 ohms. 1.8 ohms. Now they're lower resistance than these, so therefore they're going to draw more current. Goodbye!